Hello. I'm going to speak about nanobiosensors and what happened after the COVID-19. It was a global crisis, and we all have been living this very impactful situation in which there have been a lot of infected people, more than 700,000 millions, and more than 7 millions of people dead. So it was really very, very dramatic situation. It was a situation in which we also learned that how important is the diagnostics, so to perform an efficient diagnostics. So this is what I'm trying to communicate today with you, the importance of diagnostic in situations like that. So it was a situation in which the need for diagnostic tools, and in this context, point-of-care devices was very, very important. We all have been using this COVID test, which were very, very important, also real-time PCR, because this was a situation in which it was very, very important to localize the people who were infected and avoid the extension of the infection to other people. And also having this kind of diagnostic test was very important because the measurements to be taken to take vaccines was very important to know what was happening. But a very, very important issue is that this kind of diagnostic devices were having problems, and we know there are several cases in which these diagnostic devices were not working properly in terms of sensitivity, in terms of detection limit, in terms of stability, and more problems. So between these different devices, biosensors and those that integrate nanomaterials, nanotechnologies that we call nanobiosensors, are really a very, very interesting alternative to be used as a point of care. But there are problems, and why? What happened? Why so many publications and reports about nanobiosensors from the scientific community were not able to face the problem we had during the pandemics? And this is one of the issues that I would like to discuss today with you. And I think that one of the most important problems was that from scientific point of view, the proof of concept of biosensing detection principles were working fine. From scientific point of view, we had very stable proof of concept technologies, but what was missing is the collaboration with industry. Was missing the fact that we should have a higher technology readiness level technologies to be able to face the situation. And to do that, we scientists working in the laboratories, in institutes or academia in general, in universities, cannot do without the collaboration and working hand by hand with the industry. Because industry has facilities, industry has the capability to do the fabrication at large scale, and also to ensure validation, which is very, very important. Because otherwise, although you may have a fantastic technology, if it's not validated according to the procedures to go in the market, like, for example, validation in real samples, in real clinical environment or whatever, is impossible for this technology to go to the market. And this is one of the main issues that the many technologies reports by the academia were not working because they were not validating, they were not being solid and stable in large-scale fabrication. So this is one of the main issues, and this is why we should keep this in mind for further situations and possible applications in real scenarios. So what we have been trying to propose is the so-called ubiquitous fabrication. And this is one possibility important for cases of emergency. So during the COVID, we learned that the virus was changing by different places. So it was emergent to distribute the devices to the places that were needing. What about, instead of distributing the devices, to distribute all over the world fabrication facilities? But you cannot have these sophisticated fabrication possibilities, clean room, very costly technologies all over the world. What about having very, very simple fabrication facilities that I will show you in the next slides? So this is what we are willing to do. We would like to propose ubiquitous fabrication of these devices so as to face the situation and be able to produce very urgently these devices in the places that will need this. Otherwise, you have a lot of delay, because if you have to distribute the sensors, given the stability issues, you'll receive sensors, devices that will not be able to respond because of the problems related to temperature and more. So what we are doing in Barcelona, in Beaterra, and Catalan Institute of Nanoscience and Nanotechnology is trying to develop simple, cost-efficient platforms. We are trying to integrate nanomaterials, including graphene, carbon nanotubes, carbon dots, or pores into simple platforms, sustainable platforms like, for example, nitrocellulose paper, in a way that we can even stamp these materials onto any kind of surface, building very, very simple, cost-efficient devices with interest for different applications. And these can work either in electrical-based transducing or optical-based transducing, taking advantages of the interesting properties of nanomaterials. As you know, they show very interesting electrocatalytic properties, very interesting optical properties. So we can either follow the current related to the interaction of these materials, but also optical phenomena, so light coming up and down using these materials. So for these devices to be able to be used as point-of-care applications is very, very important to fulfill the criteria. We called it reassured. It means that these devices should have the capability for real-time connectivity, easy of specimen collection, affordable, sensitive, specific, user-friendly, rapid and robust, equipment-free and delivered. These are very, very important requisites. We want these requisites to be fulfilled in most of the cases, but it depends on the scenario. So this is very important. When you design a biosensor, keeping in mind what is the scenario for the application, what are the frequencies of measurements and more, in addition to the metrics, to consider before designing your sensor. And of course, as I said before, we are very much interested to work with sustainable materials, and this is why we work a lot with paper, nitrocellulose, we work with biodegradable plastic membranes. Of course, paper is very, very interesting because it is porous and you can run liquid even without any energy, so no pumping system, because the capillarity forces will pump the system, the liquid, so you can have this very nice device, very simple device, as for example, in the case of COVID test, where when you see these lines related to the plasmonics of gold nanoparticles, and the liquid is going by capillarity very in a natural mode without any pumping system. We work a lot with integration. I'll show you also, because you need to have sometimes, depending on the technology, also some electronics inside. So the market for this kind of devices is huge. This is only in the United States how this is increasing, and the demand for this kind of devices, for example, the electrical one, is huge. So starting with the first example, I'll show you 3 examples of the devices we are developing in Barcelona. So these cost-efficient devices. The first one is the lateral flow. So this is like COVID test. So I'm sure each of you have been using this at least once. And this is why during the COVID time we wrote this nature protocol to show to the community how easy it is to set up your own lateral flow, showing all the procedures you need to build your lateral flow at home, at your laboratory. So these devices, based on the paper, as I said before, are working in a very simple mode. They work like in a ELISA test, in which you have interaction of your nanoparticles, in this case, used as tags, as a signaling tool, modified with antibodies that interact with whatever you are willing to detect, for example, virus, proteins, DNA, etc., having also the control and detection lines in a way that you can detect very fast, and based on the intensity of the lines, you can correlate this with concentration of the analyte, the biomarker you want to detect. So this is a very simple technology. As you can see also in this video, it works in a simple mode, and very, very similar with ELISA test. So the sample, in this case for whole blood, is going to the membrane, and the nitrocellulose is serving as a filter. So it's also filtering, and afterwards you will have interaction inside this platform, nitrocellulose of gold nanoparticles modified with antibodies, with antigens, and you will have the revealing of the signal according to the immunosystem or whatever detection system you are following. So this is very interesting and very simple to be applied, and it's easy to build the lateral flow. The other example I would like to show is the printing of sensors. So what about printing sensors using the office printer? And this can be achieved thanks to the use of nanoparticle-based inks, and we are working with this and even patenting the technology how to achieve sintering of nanoparticles inside the ink. Because when you print with this kind of printers, it's important to have conductive electrodes, in this case transducers, and this is a case with gold nanoparticle-based inks. Based on this sintering method we have developed, you have an in situ immediate sintering of nanoparticles, so we get these conductive electrodes, and by using this we call plug-and-play technology. After designing, of course, of the sensor and printing onto the surface, wax coating and laser etching to achieve the dimensions we want. In this case, also immobilizing aptamers, we can detect, connected also with a smartphone, and this is an example of Engal, which is a very interesting biomarker for diagnostics applications, for some applications in clinical scenario. And finally, another example is that by using this simple technology of printing, we can also print wearables, and this is one recent case that we reported in collaboration with our colleagues at Catalan Institute of Nanoscience and Nanotechnology. So we're able to print this very simple wearable device for heat measurements with interest for stroke diagnostics. And here you can see how these membranes, sustainable membranes were printed using a printer, and afterwards, of course, here we integrated also the antennas, so the communication with a smartphone was achieved. So this membrane that has integrated electronics is communicating with the smartphone is giving the energy, and the wearable is giving back the signal, so we can measure different parameters. As you can see here, how this is occurring. So taking this membrane, after putting everything in the place, it is put on the hand. So we have this hand wearable device ready to measure different parameters. This is all from my side. I'd like to thank my collaborators. So this is what we do in Barcelona in relation to these cost-efficient devices that are able even to work as wearables for different applications in diagnostics, health-related diagnostics, and environmental monitoring. Thank you very much.